Okay, welcome to 1.3. We've gone through the notes. Typically, the notes are not just one video, but I think the notes were close to 13-14 minutes. A lot of explanation in here. Reminder, the information that I have on the notes is required for you to have. Therefore, I can believe that you actually listen to it, and trust me on this one, more than most any other section in the book. The notes on this one are pretty critical. It's going to give you a different perspective of how to read something like this, so it makes a little bit more sense. It's a little more visual. So let's pick it up. This page is not going to take too long, but I'm going to go through some explanation, which is going to lengthen it a little bit. First thing you need to be aware of when the book gives you a graph. Let me zoom in here just a little bit. When we get a graph, obviously a graph could go on forever. I wish that they would do this, indicate that it's continuing on, continuing on, continuing on. Now, if they want the graph to stop, it should come to just a dot. I think that makes sense. Like this graph stops, does not continue reducing below there. And interestingly enough, you're going to see a function down below that actually ends up looking like this half circle. So that's pretty important for us. And one thing, if I was asked, what is your goal of the first semester? If you just have a general goal, it would be that you can look at a variety of different functions, and we're going to see a variety of them, and have a really good idea what the graph looks like instantly. Now, obviously, when you got the graph, you've got it. But I would like you to be able to look at this function and know what it looks like instantly. Look at this one, know what it looks like. Look at 16, know what it looks like. Because the answers to almost all questions lie in the graph. So here we go. We're supposed to find the domain and range of these functions. And for domain, that's a study of the x values that live on the graph, or it's a study of the x values that we can put into here without breaking this machine. For instance, 13, we're going to have challenges close to -2. -2 is okay, but -2.1 causes a problem here. But when we have the function, all we have to do is scan from left to right. And if this continues on, there's an indication it will continue to go left and left and left and left and just incrementally move down the line. So this graph exists from -infinity and exists to infinity. So we could actually write that as -infinity to infinity. We use parentheses for infinity just because we cannot get there. We can't touch infinity. But of course, we could just name this all real numbers. And for the range, it's early morning. For the range, we scan from bottom to top, and this graph's going to go down forever. So as I scan from bottom to top, it exists as we approach -infinity going down. So from -infinity, it exists up forevermore. So our range could be -infinity to infinity. That's a scan from bottom to top. The domain's a scan from left to right. Of course, we could say that's all reals, which is probably what I would do. Number 10. This graph looks like it goes on forever to the left. As we're coming in to here, it exists right up until 0, 2, and then it jumps, but it still exists at 0. Interesting things on this graph happen at 0. It jumps down here and exists forevermore. So it exists to the left forever, right forever. So coming in from the left, the domain it skips from here to here, but all x values are represented in this graph, so all real numbers. However, the range, as we scan from bottom to top, does not exist until we get up here to -3. And it does exist at -3, and it appears as though it continues to exist with the arrows doesn't just appear. It continues to exist and then kind of doubly exists here forevermore. So there's interval notation, which we're going to end up preferring. You could certainly say for this that f of x, it is f of x, is greater than or equal to -3. I would accept either of those. Okay, use a graphing calculator to find the graphing calculator to graph the function and estimate its domain and range. So these problems are exactly like the top. Then it says, then find the domain and range algebraically. I'm going to just have you find the range with your calculator, but I'm going to talk to you because it's really not an algebraic process for finding the range. It's a little deeper than that. So I'm going to talk you through that, though. But to say we're doing it algebraically would be false. Okay. So let's go ahead and graph this. And this would most certainly be, if you don't know what the graph of this looks like already, that's perfectly understandable. But I'll tell you what, in a week you will. You can look at that. Oh, immediately sketch it. All right. So let's clear this out. That's a later problem. And let's go ahead and go square, whoop, wrong one, x squared minus 1. And I generally like to start in Zoom Standard. I'm not sure what my calculator's set in right now. That is Zoom Standard. So I could go ahead and hit graph, but kind of a habit I'm in. I just hit Zoom 6. 6 starts with S, Standard S. Zoom 6. So there's my graph. On these problems, when you're to use your graphing calculator, create a graph, I would like you to do that on your calculator, but then go ahead and sketch what the graph looks like. So I feel like you've actually done that. And then let's take a look. Domain, it appears like this can go to the right forever, to the left forever. And this says to estimate. Because in all honesty, how do we really know it doesn't just eventually get virtually vertical and quit going to the right? We'll have some graphs like that. So we just have to estimate. But I believe it can go to the right forever. So our domain from the left coming to the right, scanning, I think it exists forever. My range, however, looks like as I scan from bottom to top, it doesn't exist until about -1. Let's take a look. I'm going to go second calc, and I'm going to ask for the minimum value in this graph. So I know it's to the right of here, so this is a left bound. Hit enter. Now it's asking me to get to the right of the minimum. Okay, I know I'm to the right of it. Hit enter. Hit enter again. And it says that the minimum y value occurs at -1. And this guy right here, this will pop up in our calculators a lot. -1.724 times 10 to the -6. That's -0.000017. That is virtually 0, and it is 0. Okay, but anyway, our range as we scan from bottom to top starts to exist at -1, including, that's why it's a bracket, including -1 to infinity. Or we could say f of x is greater than or equal to -1. Now, the algebraic process for this one's pretty straightforward, but we ask ourselves, can I square any number? So for domain, can I square any number I want? Yeah, I can square positives, I can square negatives, I can square 0. Can I subtract 1 from any number? Yeah, you give me a number, and I can subtract 1 from it. So that means there are no bad values for x. So that just verifies that this is our domain. Now, as far as the range doing that, and I said it's not really an algebraic process, you're going to hear me talk about, and I think I've mentioned this in a video before, MyVox, the most interesting value of x. Now, when we think about squaring a number, if I square a number, I always get a positive. unless x is 0. So the smallest this value can be is 0, and that happens when x is 0. Zeros are my vox. When I put in 0, I get -1. I get 0 minus 1. So if x is always going to be bigger than 0 other than that case, then -1 is our minimum, and our range is -1 to infinity. So it's more of a discussion that leads to it. You'll see the algebra in play for the domain on number 14. Okay, let's go ahead and get our graph for 14. Y equals clear is a nice option. Square root is right here on blue, x squared, or second x squared. 4 minus x squared. And we'll go ahead and graph that. I'm already in Zoom Standard. Let's see what that looks like. Oh, and I think I mentioned earlier that we're going to have a graph that looks like that number 9. Not exactly, but it looks like number 9. It looks like it goes over to about 2 here and up to 2. Looks like a semicircle. Well, actually, it looks more like an ellipse, but that's because these X tick marks are closer together than Y. It's stretched out here. But it looks kind of like half of a circle. In fact, it is. But my graph shows that, wow, maybe it doesn't really come down. Maybe let's see if you can see this. See how it kind of just stops here, up in here. So one thing we might be tempted to do is go to trace, and as I trace over, the graph exists, I'm at 1.8, 1.96, then I step over 2, and it doesn't exist. And the thought is, well, maybe it does exist at 2, the graph just stepped over. So I'd like to have smaller tick marks, or I can do a study with it, or I can say, hey, I think it probably exists at 2, and I can go, as I'm tracing, I can just type in 2, and 2, 0 is actually on the graph. And how about if I type in 2.00001, and now the graph doesn't exist. So I believe for our domain based on the graph, which I need to sketch in here, as do you. Scan left to right. I believe it exists at -2. Well, it does. And to 2. The algebraic, we'll come back to algebraic. And the range looks like it is 0 up to 2. And I could put in 0 here. And we do get 2, and it looks like that's the highest it gets. Now, our domain could also be -2 is less than or equal to x is less than or equal to 2, and our range could also be 0 is less than or equal to, oh, this should be a t, since we're dealing with t here. 0 is less than or equal to h of t is less than or equal to 2. Okay, so algebraically, can I square any number I want? Yes. Can I subtract any number I want from 4? Yes. Can I take the square root of any number? No. 4 minus t squared has to be at least 0. So let's see when it is 0. 4 minus t squared equals 0. That's 4 equals t squared, or t squared equals 4. Now this is a dangerous point right here. I will ask, like if in a classroom setting, I would now ask, how do we rescue that squared? How do we get rid of a squared? And I will always, for a month to 2 months, someone will say, and usually it's a chorus. I mean, you get a number of people saying different things, but I will always hear some people say, I go, how do you get rid of a squared? And they'll say, with a square root. But it's not just a square root. This says what number times itself equals 4, and there's 2 answers. And I will always emphasize, I'll say, not just a square root, a plus or minus square root. So t equals plus or minus 2. Those are some interesting values of t. That's my myvat, or my myvats. since there's two of them. T equals plus or minus 2. So let's see. On a number line, I put in 2, I put in negative 2. Those are good values, but barely. And then if I put in 0, something between those, 4 minus 0, square root of 4, that's fine. This is a good zone. If I put in 3, something beyond 2, 4 minus 9, that is not a good zone. Put in negative 3, it's the same as putting in 3, which implies on this graph, the height to the left is the same as the height to the right. Oh, when I put in a negative, the left side of the graph should look just like the right side. When I put in a negative, it's the same as putting in a positive. So anyway, we get this, which confirms our domain. Okay, one more here, number 16. I'd like to, this would be where I'd probably throw out an extra credit, not an extra credit point, but toss out a Jolly Rancher for the first person who got this one right. I'm looking at number 16. What is the MIVOX? When I take an absolute value of a number, I always get a positive, except when I get 0. And hopefully, for MIVOX, when I asked what is a MIVOX, you said, oh, the most interesting value of x, therefore, is 5 because it gives us absolute value of 0. Otherwise, this is going to get bigger in both directions. Okay, so let's go ahead to the graph. Clear? You can enter this as negative 0.25. You could enter it as negative 1 divided by 4. I'm going to try to encourage you to get in the habit of, let's use that fraction key. So I've got negative 1 on 4. And then absolute value, you can find absolute value in the catalog, which is second catalog. And you're in luck because alphabetically absolute value comes early. But it's used so often that this F2 right here, function 2, which is alpha F2, these are the ones, I think there was a previous mention of this in this course or in this video, where our very, very commonly used functions from our catalog are put together here for us. So absolute value, x minus 5, I graph that, and take a look. There we are. We have a graph. We put in 5, it looks like 0. And verifiable right here, 1, 2, 3, 4, 5. It's kind of flat this way, kind of flat that way. So our domain, it appears as though this graph's going to go on forever to the left. So coming in from negative infinity, it never stops. Most interesting value of x occurs at 5. And so our domain is either negative infinity to infinity or all reals. Our range, I believe this is going to go down forever, so I believe eventually the graph's going to exist down to negative infinity, comes up and stops existing, not at 5, this is y's, from negative infinity up to 0. So that's negative infinity, can't get to negative infinity, parenthesis, up to 0. We actually do get to 0 in this case. Or f of x is less than or equal to 0. Either of those answers, we're moving to a place where we'd actually prefer that. Okay, there you have it. I'm very confident that you will get through 7 through 15 much quicker than I did with all the explanation going on, but isn't that the way it's supposed to be? Good luck. Let me know if I can help.